emerged. And so the Pope asked, okay, in this wall, I will put all my books regarding this topic. And so this is the subject of the painting. And so you see a lot of scientists, philosophers, and actually at the center of the fresco, there are two figures, Plato and Aristotle. Because at that period, we're speaking 1500, 12, 13, something like that, Raffaello was 23 years old, very young. And there was still a huge debate between the followers of Plato and Aristotle. Plato was, as you know, proposing the supremacy of the idea, so he's indicating the stars, while Aristotle is pointing out that it is necessary to refer and rely on our experience, so on observation. We will see that there are models based on the theoretical approach, let's say, while other models are based on the data, let's say more statistical models. So even nowadays, somehow in there is a kind of debate and discussion, which is not the case. Actually, because we can stay in Rome after 1 century. Galileo solved this issue. It was not possible when Raphael was living, but Galileo clearly explained that there's a link between the theory and the observation, and we need to prove the theory based on our experiments, and in case if we should change our theory. And this actually is at the basis, later on has been further elaborated by the English school, Hume. So the process of induction from data to the theory and deduction, the other part of this circle, of this flow of information. In the case of in silico model, we have data for free. In the case of Rina Cross, these are virtual data, so related substances. And the software, it can generate a kind of theory, hypothetical mechanism. So we can imagine a parallel process, a virtual process, and the flow of knowledge from data to the theory and then back. Thanks, in this case, to the computer. And actually, even later on, last century, this fundamental study and scientific position regarding the uncertainty and the probability. So the need to evaluate each process, each phenomenon in terms of probability. So remember these 4 guys, because these are fundamental for our evaluation of in silico models. The experience, Aristotle, the data, the observation, the theoretical part, and the need to have a dialogue between these two, ideally not a conflict between the two. And it is very important also always to remember the probability and the associated uncertainty. So that these guys should drive us in the evaluation, not only of the silico model, but in particular in our course, these are fundamental, and but I use it for also in other fields, in vitro and so on. In silico, in 2001, the New York Times wrote, okay, all science is computer science. And nowadays, after 25 years, even more, think about generative AI and all the process which been generated since the last few years, also we can say. So this is something that actually goes beyond, of course, the use of the silico model for chemical evaluation, but in all our experiments, this is a fundamental piece. But let's speak in particular regarding the case of the in silico model for chemistry and what we call in silico model for the evaluation of the chemical substances. We start from data, always. Typically, the human experts are evaluating the data, and then they understand something and elaborate a theory. The same process can be done by the computer. So also the computer is using data, experiments, results from our toxicological studies. And indeed, the data are at the basis of the silico model. And we speak about intrinsic knowledge, because this is inside the data, or explicit knowledge when this, for instance, is theoretically described by the human. There are some difficulties, say disadvantages, and skepticism, because in silico model indeed are something which the model exists, but the data in some cases the assessor are somehow skeptical, because indeed they are not directly based on experiments. So there's this skepticism based on the traditional experience to rely on observation, on experiments regarding toxicity. This is true, definitely, necessarily, but there are some advantages which are unique of in silico model. So they can learn. They can generate, as we already anticipated, proposition. Let's think about the common way to process and evaluate toxicity using in vivo, some cases also in vitro studies. So there have been tens of thousands already registered for REACH. And if you want to register a new chemical, this is the way to be done. So you have to repeat the same process. And after 1 million of registration, you have to repeat the same process. So this process is blind. There's no possibility to learn, to understand what we're doing. In silico model are heuristic, so they can learn from the past, but not the usual in vivo, in vitro, omic data. They do not learn. So this is really fundamental. The complexity, we can cope with many processes at the same time. Let's consider this point is a metabolic network of Escherichia coli. And if you want to describe all the possibilities, you easily arrive to tens of millions of possibilities. And of course, you cannot investigate manually each of them. The possibility to use probability inside the computer models, and this is something very important. In many cases, if you don't have this possibility, you have a certain feature, I don't know, the other group, and you can say, okay, this will be mutagenic. Actually, only 50% of the dyes are mutagenic. High cardinality. So using the Vega model, we will use the Vega model. In the past, we calculated properties of 6 million substances. It is impossible to do the same using in vivo, in vitro omics, in chemical, or whatever. The fast dissemination. So when we put Vega new model, immediately this can be utilized as all part of the world. We're speaking about the virtuals. We say that this is a disadvantage, but it is also advantage because we do not need physically the substance to make the experiment. It's simply to imagine, to draw the computer the substance, and we can anticipate some properties. So this is something, for instance, good for safe and sustainable by design within PARC. And we do not use solvents anymore, so we have no waste. It's quite green, of course, with some power, some electricity not necessary for the computer, depending on the software for the Vega model. We don't need quantum computing, so no necessity for low temperature. And well, it depends on the model. The models that we will use and many other models are free, available. There are also commercial models, but this is free. And again, this is not always easy to let's say, have models or way to evaluate the chemical at no cost. So this is actually an advantage. We can cope with many different properties at the same time. So not only one. If typically when you make an experiment, you make an experiment for that particular endpoint. In the case of a silico model, you ask the computer to make 1 or 10 or 100 or 1,000 different, and the computer does complain. So this is also useful in case of screening, prioritization, so you can cope with multiple properties. So we will see in our course environmental properties, but we can deal with exposure and so arrive immediately to risk assessment. And this again is quite useful, particularly in the case of safety and sustainable by design, because safety is not simply lack of one adverse property, but multiple adverse properties. So overall, to summarize what we have seen, there are some unique features of in silico model, generally speaking. I think the key point is that they can learn, so they can anticipate the possible, probable, it depends on the uncertainty associated to the results, feature properties of the chemical or the multiple chemicals which you are interested in. They can address complexity of phenomena, while our brain, our experience quite often is limited to 1, 2, 3 steps, but not many after. We can evaluate the probability and not just rough, okay, more or less, but we have quite a good estimate. We can use the tools for screening, prioritization, so a large number of chemicals. And this is a necessity nowadays because there are hundreds of thousands of chemicals we're exposed to. The system is quite fast, surely faster than all the other way to evaluate the chemical substances, where we can wrap multiple characteristic. In this course, this is a kind of quite course, preliminary initial course, and we will cope with hazard and this kind of property, but exposure, you can also evaluate exposure, and so you can reach risk assessment. Tomorrow, actually, we will see Gianluca will show in particular the case of risk assessment of cosmetics I hope he will recover his little bit of flu. Uh, I mentioned a faster dissemination. So we can have this kind of course with people in Europe, in principle around the world, that may be more difficult in our cases for physical, say, training. And we do not produce the waste, we do not consume chemicals. This is free. And it copes with multiple property characteristics, also addressing the mechanism beyond what we're exploring. I think that this is the general introduction. I don't know if you have questions regarding this.
There's an interesting question in the chat. Let's say, I don't know if you would like to read it or I did it for you.
Yes, please.
Okay, you say that an in silico model can learn unlike an in vitro model. Would you consider an issue that an in silico model is not naive like a cell or a rat would be? May that lead to misconception or even errors when it comes to highlight unusual patterns of toxicity or mode of actions, for example?
Well, if you are using a cell, you have no possibility at all to anticipate the effect if you consider that chemical. So you are in the situation of, let's say, 50-50. Is it toxic or not? I don't know. So I make the experiment. If I use in silico model, I can anticipate and I can explore. We will see example, and I can focus our we can focus our attention to a particular part of a chemical which maybe is associated to the toxic, the adverse behavior. And so we can analyze the behavior of similar related chemicals. And so it may be that while we analyze this kind of behavior, we can this can help the possibility to, let's say, identify the possible mechanism, because, I don't know, all chemicals which are toxic, so I don't know, if, let's make an example. We studied coumarins, and roughly, let's say, half of them are genotoxic, and half of them are not genotoxic. So we have identified a particular, if a presence in a certain position, 7 position, there was an oxygen. For instance, this kind of chemicals were not mutagenic. And this can be explained because at this point there is a different parallel process leading to detoxification, because if you have that oxygen, this will facilitate the conjugation, so the excretion, and so this process is faster than the attack to the double bond leading to epoxide and so genotoxicity. So this, observing this, you can generate the property, but depending on the tools, some tools also can investigate the distribution of the charges and the possibility to have an attack, a nucleophilic cathode or any other kind of reactivity in a particular kind of position. And so this indeed goes beyond the simple observation, because you can anticipate the behavior of that chemical. So I don't know if this example can help to clarify what I mean with learning. Okay. So maybe it's my turn to introduce Alessandra. And Alessandra also, actually also presented our of Istituto Barionesi, so it's quite easy to identify the affiliation of the speakers. And she's the head of a laboratory specifically dealing with in silico models. So she will speak about entering more into the detail of what we're speaking about, while this was quite a general introduction.
Thank you, Emilia. I'll share my screen now, and if it's working. Okay, I have also my presentation already here. Okay, so good morning, everyone. Now I will give you a little bit more technical details how usually models are developed, and as well as the main and key characteristics and issue that has to be taken into account for the regulatory acceptance of QSAR models. So, first of all, just to let's say clarify a little bit, because we usually speak about in silico models, but indeed there are a variety of different in silico models. In this course, we will focus mainly on QSAR and read-across, while if you are familiar, for instance, with drug design, you may have I've heard about 3D or structure-based modeling in constant to 2D or ligand-based modeling. So with 3D or structure-based modeling, you mainly study the direct interaction between macromolecules and small molecules or among different types of macromolecules by using, for instance, virtual docking and molecular dynamic simulations. In the case of ligand-based modeling, you simply focus on the ligands or the chemicals that may bind to a specific receptor or may have a different type of effects, ignoring or regardless the knowledge about specific target interactions. There is the QSAR technique, 3D QSAR, that is more related to specific target analysis, structural or expert rules, and as well as read-across. So the basis of the QSAR or QSPR paradigm is that a quantitative structure-activity relationship is a model that relates a quantitative measure of chemical structure to a physical properties, and in this case is often called QSPR, or to a biological effect such as a toxicological endpoint, and so usually it's called more properly QSAR. And the assumption behind that is that the activity that you are investigating is a function of the chemical structure itself. Basically, the postulate is that the molecular structure is responsible for the activities, and similar compounds have similar biological and physical chemical properties. You will see that over the course, and also when we will deal about a read-across, the concept of similarity becomes very pivotal in this regard. And sorry, just to show you that QSAR, it's not a new technique, so it was already active in the from half of decades of the last century, and at the beginning, especially the QSAR approach was applied mainly to congeneric series of similar molecules, investigating basic biological activities, and and by using as descriptors for so independent variable for the model a small number of intuitive properties, investigating mainly linear relation, and usually there was not a lot of emphasis on the validation aspect, because the models were more meant to be descriptive of a certain behavior he was observing among a congeneric series of chemicals rather than predictive for new chemicals. Over the time, this approach became a little bit more complex, also thanks to the increasing availability of hardware and software solutions. So heterogeneous sets of compound has been investigated, focused on either complex endpoints and mixed mode of action together, and using as predictors large number of properties and nonlinear modeling methods. And the emphasis on the validation increased a lot. Nowadays, of course, there's also AI, so the techniques became more and more sophisticated, so machine learning and deep learning approaches. At the same time, rather than targeting directly very complex endpoints like carcinogenicity and mutagenicity in the most recent years, there was also an interest to go back to, let's say, simpler endpoints like the MIEs and key events of the AOPs. So to use QSAR in support of the AOP framework and the next generation risk assessment. And also sometimes descriptors have been expanded from being strictly chemistry oriented to including also some information more biological oriented, for instance using as descriptors information gained from omics experiments. And there is also an emphasis towards open source software and tools that can be used by a larger number of people. So just about the classical building blocks in the QSAR approach, basically, as explained before, the idea is to find a proper relationship between the molecular structure and an activity, which can be a toxicity or, I don't know, a specific receptor affinity or whatsoever. For doing that, you would require a matrix of data that basically consists of a X matrix of independent variables, which are the molecular descriptors calculated over the structure, and the response or responses variables that describe the activity you wish to assess through the QSAR model. Through a statistical analysis, so different algorithms and validation of these models, you can get a prediction for the original property. So the first part related to the calculation of molecular descriptors, that are numerical values that characterize the properties of the molecules. For example, there can be simple or very intuitive physical chemical properties, which may also be empirical descriptors, or values that are calculated from the algorithm, such as 2D fingerprints or other descriptors. They can vary in terms of the complexity of the encoded information and in computed time, but it can be also, let's say, experimental values arising from previous experiments. For instance, the log P or log KOW, so the partition coefficient between octanol and water, is a very commonly used descriptor for modeling aquatic toxicity endpoints. Of course, whenever you rely on experimentally determined descriptors, that implies that you will be able to use that model just for chemicals for which this parameter has been already tested, and it's not possible to use them for any, let's say, compounds prior to the synthesis. As Emilio already introduced, type of possible descriptors that is also quite intuitive one, and is based on the ability of human expert to identify specific substructures that are responsible for toxicity, and usually this kind of descriptors, which are very important for some types of toxicity, for instance genotoxic effects, are called structural alerts. On the other hand, there are descriptors, as I said, that can be calculated by algorithms and applying some different calculation on the chemical structure. But at that point, you need to, first of all, move from, let's say, the real chemical compound that can be also a mixture or including impurities, to its structural representation, which again it's a kind of model of the structure, because you may see here that there are different types, ways to define the chemical structure, some very compact one, like the SMILE string, or more or less sophisticated, so 2D structures, or 3D structures, or even some analysis over the influence that the 3D structure has on the surrounding environments. And on this basis, you may calculate the chemical descriptors through the help of different softwares. A classical way to, there are nowadays there are thousands of descriptors plus fingerprints, and a common way to classify them is depending on the complexity of the required structural information to calculate them. So descriptors that are called 2D descriptors are derived mainly from the atomic composition and connectivity of the molecules, while 3D descriptors may encode also for energetic and spatial information of the arrangement of the molecule. There are also some extended or more advanced descriptors that are usually were referred, especially in the past, as molecular interaction fields, and that encode in general for electrostatic and steric variation around the space of the molecule. The main group of descriptors that is usually employed are 2D descriptors, because there are many groups accounting for different characteristics. So there are constitutional descriptors that describes the number of atoms, bonds, specific rings, and so on. Topological descriptors that may calculate topological distances in the molecules, and a lot of descriptors that are calculated over the matrix of the structure itself. And the advantage is that they are fast to be calculated, and many of the expert systems usually rely on such a type of descriptors. For instance, Vega employs mainly 2D descriptors, and they are more reproducible because they do not require the three-dimensional structural optimization. That implies that somehow the number of bonds, the number of atoms in a molecule is not depending on the shape of the molecule itself into the three-dimensional space. On the other hand, it can be that they are more focused on local contribution, somehow neglecting or being less capable of encoding for the intramolecular interactions, and they ignore, of course, the conformational flexibility of the molecules. So they do not take often into account the steady configuration, and they are not invariant to tautomerism. That implies that if a chemical may exist in different tautomeric forms, you have to, you may come out with different numbers for some of the descriptors for the same chemical itself. So in this chart, you may see that 2D descriptors are made, may distinguish constitutional isomers, but not conformational or genetic isomers, or the stereoisomers. Okay. 3D descriptors, start again, are instead calculated on the optimized 3D structure, and they are invariant to the translational changing, but they may require conformational search followed by quantum mechanics or molecular mechanics optimization. This is to find a kind of reference substance, so to use the minimum energy structure for the calculation of the descriptor. This is anyhow a reference structure because we are looking for, let's say, the most stable conformers, but usually this kind of optimization is done in the vacuum. So it's not completely somehow reflecting what's going to happen when the molecule enters the biota, or I don't know, the cytoplasm, or any, or when there will be a liquid or something interfering, or that can influence the energetically more stable conformation. And another point is that, as I was mentioning, compared to the descriptors, is that the 3D descriptors are more susceptible of variability between different methods, so using different optimization approaches. There are also some stochastic steps that may play a role there in finding the most suitable conformation. And as well as another point is that the same descriptors calculated by different software may use some slightly different algorithms, so come out with different values. Here there are just two very old examples, but where the same parameter has been calculated with different software, and there is a 3D descriptors, and there is a kind of difference between the value that is given back by the two different software. As well as I was saying, if you are using a chemical structure, optimizing it, and then you redo the process, you will have somehow a kind of reasonable alignment, but there are also some outliers because the stochastic process may have given a different final structure for the calculation of the descriptor. So, depending if you are using 2D descriptors or 3D descriptors, the point is that you would need a matrix of n compounds and a number of descriptors up to m, and a matrix where for the same compound you have an activity or multiple activities, if you like. And the idea is to find, as I said, the best function that describes the relationship between these descriptors and the activity. Usually, as I said, the acronym QSAR, QSPR, sometimes I saw also QSTR, so and all of them are defined by the activity data that you are going to model. So in case of quantitative structure property relationship, we are studying physical, chemical, or biochemical properties like boiling point, partition coefficients, or persistence, while for quantitative structure activity relationship, usually you consider ecotoxicity or bioactivity for specific effects, or mechanistic assays, and so on, as well as sometimes the term QSTR when you focus on toxicity. The first step Now I show you very quickly how to generate your matrix of data, but the first step is data curation for the activity data and the chemical structure. Data curation for the activity data implies that you need to gather a set of compounds with an experimentally determined activity data you wish to model. And so the quality and quantity of available data will define the modeling strategy. Of course, gathering data from you may also do, let's say, experiments, but since usually we would like to use large data sets, sometimes it's easier to, let's say, collect and gather data from literature, and at that point you need to realize whether the data are suitable for purposes. So if that specific readout you wish to model is the one that it's interesting for I don't know, the toxicity you're studying, or if there may be some artifacts that are going to make the readout unsuitable for specific chemical classes and so on. And so at this point it's very good to talk to experimentalists and really understand which type of data are going to model. Of course, it's also important to consider that there's still an intrinsic variability in the experimental values or biological, that may be driven by the biological variability or by the experimental setting, and that there will be a specific chemical domain may be covered with the experimental data. So, for instance, usually drugs are more data rich compared to other category of chemicals, for instance, natural compounds, because they are more heavily tested, and so this will influence also, let's say, the validity and the possibility to apply the model that you derived on such a kind of data to future chemicals. At the same time, so if you have to take care of preparing a good data set for the, let's say, predicted, for the property you wish to predict, at the same time there are some standard procedure for data curation for the chemical structure. So to define which chemical structure can be included in the data set. For instance, usually we neglect inorganic compounds, and so they are not, let's say, the best candidate for QSAS, because most of the software are not able to calculate properly the descriptors on inorganics. For salts, we modify the structure usually, and we consider just the free acid part. And then, of course, there's the issue of mixtures or impurities, because, as you have seen, usually the descriptors are calculated on a single well-identified chemical structures. Of course, nowadays there are also ways, and there are possibilities to handle such a kind of situation, but let's say that usually the first thing is just to identify which kind of chemicals are going to be included in the data set, and if you don't need specific models for mixture or salts and so on, the standard procedure is to use a unique chemical structure and descriptors calculated on this chemical structure. The modeling step then consists on the data preprocessing that try to understand if there is a kind of relationship into in the data, or let's say also making some preliminary analysis of the data distribution, and especially understanding if it's possible to apply some transformation to the response variable to increase the linearity of the distribution of the data, because that will help in finding a reasonable results, reasonable and good statistical quality results. There's variable pruning, so variable that implies that to dismiss irrelevant variables, so variables that are always constant, for instance. And then the next step is to reduce the number of variables, also to variable selection, so reducing the dimension and facilitating data visualization and interpretation. This will also likely improve the prediction performance, and the variable selection in the past was often hypothesis driven. As I said, if you're addressing aquatic toxicity, you will probably include log KUW as a relevant variable, but it may also be statistically driven. Then, of course, you apply the different algorithms to search for the relationship, and the validation process is quite essential. So usually it's not, let's say, there's not general consensus, but usually as a SAR, so structure activity relationship, describe all the, let's say, qualitative approaches. So when you somehow associate the presence of a certain fragment to a specific activity, but without any quantification of this association. On the contrary, with the term QSAR, so quantitative SAR, you can anyhow handle both classification or regression problems. So whenever you have a continuous value, you have a regression problem. So the modeling algorithm is going to find the best relationship with a quantitative activity, or it can be a categorical activity, and so you will have a classification model in 2 or more classes. Okay, so for the algorithms, nowadays they are really there are too much to, let's say, include them in a 1-hour presentation and overview. And for instance, in Vega, different models are based on different algorithms, because every time we come out with a different data sets, maybe one strategy is best than another one. And so just bear in mind that the choice of the algorithm is depending on data availability in terms of either descriptors and the size of the data set, the number of chemicals you may have there, and the type of response required. So if for, let's say, your purposes, it's more relevant to have a quantitative or non-quantitative models. There are, in the past, there have been often used a lot of linear methods, and nowadays as well, and there are nowadays a lot of nonlinear methods that can be also employed either for regression or classification problems. What is important also for linear methods, but especially for nonlinear methods, is that there's this process of optimization of the model parameters, for instance, that can be based on different approaches, and the selection of the of the appropriate parameters to optimize the model is quite important to have then a good resolution, a good capability of discrimination in the model itself, especially for classification models. But I'll enter a bit more in details in a couple of slides on that. For continuous models, there are standard parameters that calculate the difference between the observed and predicted values in terms of root mean square error, mean absolute error, or also with the correlation coefficient. Classifier, especially the majority of models usually are binary classifiers, so it's easy to have a class of positive and negative, and so in this case the metrics are based on mainly based on the confusion matrix, where you can investigate accuracy, sensitivity, and specificity. And there are many more nowadays, especially with AI and machine learning machine learning methods, many other statistical parameters may be calculated, but it's important especially to take care of whenever you are using binary classification, you have to understand if your data set is highly unbalanced towards one of the two classes, because these parameters may not be the best one to evaluate and assess a model on binary class, on binary for binary classification of unbalanced data sets. And for instance, a very easy metrics to be used can be the balance accuracy or also the Matthew correlation coefficient, because in that case the errors in the less represented class are weighted more heavily compared to the errors in the more abundant, in the most abundant class. That's because if you have a quite unbalanced data set, you can have an accuracy close to, if you just have as a response the most abundant class, this will become your accuracy overall, even though the model is completely unuseful, because it will always point to the most abundant class. There are also ways to handle such a kind of data set. So whenever you have an unbalanced distribution in your data set, you can exclude some of the sample from the most represented class, and this is called undersampling. Or you can replicate with synthetic examples the less abundant class, and this is usually called oversampling. Now let's move to the issue of validation. There are different types of errors in models. There can be a bias, so the errors due to inaccurate assumption or simplification made by the model due to what is given as training set, and there is variance, that is how much the model estimated from different training sets different from each other. The two specific issues, the specific issue that has to be underlined during developing QSAR is overfitting specifically, because with underfitting you have a model that is too simple to represent all the relevant characteristics, so you can have a high variance and low variance, and high training error and high test error. On the contrary, when you have overfitting, the model is too complex and it fits also irrelevant characteristics like such as the noise in the data or the variability, the intrinsic biological variability. So you will have a low bias but high variance in this kind of example, and low training error and high test error. This is what usually may occur, and this is a kind of, let's say, interactive explanation of the process. So let's imagine that we are analyzing an experimental activity, and we decide to look for the best relationship with one single descriptor. You may have a very simple linear relationship that somehow nicely describes the trend of this point of your, so these are your 6 chemicals with these 6 descriptors value, and you can have a very good agreement, and you may find a very a satisfactory relationship. If you may also instead try to be more precise and have a polynomial relationship describing the variation, the experimental activity starting from this descriptor, and in this case you see that the R square, so the precision in the description of the trend, it's much higher. But if your goal is to predict now these 2 new compounds that have never been tested before, and for them you have these 2 values for these descriptors, you may see that the error, if you use this model for predicting these 2 chemicals, it's much lower if compared to the error you may observe if you are using the polynomial model. This is a too complex model compared to the capability of generalize the trend in toxicity. So if you are trying to have a zero error, you are likely doing an overfitting to the training set data, but whenever you are going to use that model to predict new chemicals, you will have a poor generalization, and so the errors will be higher. On the contrary, in the good balance, you will have a relationship that describes the general trend, and this general trend will have, let's say, higher error for the training set data, but lower error for the test set data. That's exactly what's gonna happen for optimizing the model and to search for the best relationship. There are different ways to validate and so to estimate the possibility of a model to predict new compounds, and the simplest one is to do cross-validation. So starting from your set, you leave for the leave one out cross-validation, you just keep aside one of your compound and develop the model and predict the excluded compounds, and you repeat it for all the samples, and at this point you may calculate the Q squared or R squared cross-validated, or with the same approach as the R squared on the basis of the predicted cross-validated value. The issue is that usually, especially if you have many samples, this is a too optimistic way, because the perturbation you are introducing into the model is very small, and a more robust way is to use a leave many out approach, so to exclude every time not just one chemical but a subset of compounds, and until all the compounds are excluded iteratively once. The issue with cross-validation, you will have a unique parameter, because even though the compounds are set aside randomly, they can be set aside randomly, they are excluded just once. So there could be that just by chance you will have a higher or lower number for these R squared. With bootstrapping, you do a similar thing, but you repeat this resampling, so the exclusion of a subset of chemicals multiple times. And so you will have a distribution, because maybe some of the samples are more relevant, can be the attractor in the relationship, and so by excluding them, the relationship will change more dramatically. And so with the bootstrap, you exclude a subset of objects and repeat this iteratively for a number of times, I don't know, hundreds of times, and so you will have a square or different parameters, MIEs or RMSE, calculated each time, and then you will have also a distribution of the accuracy that is obtained by the average of all these calculated statistics. There's also the possibility to randomly to introduce a random permutation on the Y response while the predictors are kept in the same order, and by again iteratively adopting this approach, it should happen that whenever you are using a very different data set, so whenever your new variables are very different from the previous one, you should have bad statistics. Otherwise, it's let's say again a signal of chance correlation in the data set. Another important thing is that whenever you're using R squared, in reality you are looking to the correlation coefficient. So yeah, any relationship that is close to that is linear will come with a good R-square. But at the same time, since you are trying to predict the exact value of a parameter of an activity, you have to ensure that your predictions are close to the one-to-one line, so the bisectrix in the graph. And so there are a number of possibilities of parameters that you can check to verify the fitting and the distance to the bisectrix in your relationship, both on the cross-validated parameters, so internally to the training set, or to an external test set. In general, so just to summarize, to discuss about the model performance, you should focus on the robustness of the model, that are all the parameters that you can somehow leverage on the training set data. So internal validation process like leave one out, leave somehow, bootstrap or was scrambling. Predictionability is usually assessed through a prediction on an external set. That it's usually called a test set, but it can be called validation set or prediction set. And if it's a classification model, at that point you can reason about false positive and false negatives there. But the essential part is that this set can be can have, I mean, it's complex and it's not always clustered in the same way. Usually it's a set of compounds taken out from the training set at the very beginning, so prior to variable selection and model optimization. And it can be set as it can be derived in a random way, or trying to maintain the similar characteristics to the training set distribution. Or it can also be something, or let's say in the most drastic and so the most real life situation, it can also be a set of compounds that have been released afterwards, and this will really be a set of chemicals that is completely unrelated to the training set, the original training set. The last point is about the applicability domain. I've never mentioned this till here, but the applicability domain is the chemical and response space where the model can be applied. That's why because also from the validation and so on, you are always looking to general population of chemicals. While it's likely that there are some chemicals that are better predicted compared to others. It might be that some classes are less represented, and so the algorithm is not capable of extracting the relevant information to properly describe these subclasses, or maybe the toxicity mechanisms are so different, and so they escape from the relationship that is instead valid for the rest of them. So the applicability domain of a QSAR model is defined as the response and chemical structure space in which the model makes predictions with a given reliability. Basically, you cannot argue if a prediction that is you have no ways to infer if a prediction out of the applicability domain is reliable or not per se, but the definition of the applicability domain has become central to QSAR because the chemicals that are within the applicability domain are coming with a prediction that should be more reliable. Usually the key concept again is related to the similarity, for instance to the training data, because if you come with different examples, this is a kind of a very colorful example, completely unrelated, but where you have a population of training data that were some flowers, but just tulips, different colors. While among your new chemicals, there were tulips, but roses too. And for the second group, of course, it's hard to, let's say, estimate that the model can give a good prediction. In general, there is no general consensus on how to define the applicability domain of the model. You will see that in Vega we are using multiple instances, exactly to ensure that all the possible information is taken into account, but some part of the information regards the similarity measures with the training data, so analyzing the response range, the span of the activity data in the original training set, chemiometric treatment on the descriptor space, so the global descriptors that has been calculated at the beginning, or the reduced set that is used within the models, fragment-based approach where you can identify rare or rare fragments or underrepresented fragments, and so it could be difficult to argue about the relevance and the behavior of that specific fragment in modulating a specific effect, as well as considering the model's characteristics. As I said, maybe a model is not capable of providing good prediction for all the chemicals, but according to the algorithms, you may have some areas where the prediction is closer to the experimental values, and other cases where the prediction is much far away, and so the model itself and the prediction and analyzing whether the model is capable of giving good predictions for similar chemicals, it's quite interesting and useful to define if the model is working well or not in a specific narrow chemical space. That said, I would like, this was a kind of let's say theory about how to develop a robust QSAR model, and you will see that in Vega we have a number of them already implemented. At the same time, since PARC is mainly focused on risk assessment, it's very important also to ensure that any kind of prediction, even being reliable, because the model is robust, based on good values and so on, it can be also, it should be also fit for purpose, for regulatory purposes. Reach nicely sum up the main characteristics for QSAR being used, for instance, for registration purposes, but I simply deleted one slide, but a very similar characteristics have been also pointed out in some EFSA opinions and so on. Anyhow, a model for being valid, so compared to in vitro tests where we often see the term validated, we consider, here we focus on the validity of the model, not on the validation of the model. The model has to be recognized scientifically valid, so to ensure all the things I've gone through in the previous 45 minutes about how to properly develop a good model and a reliable model, so scientifically valid. The substance you wish to predict is included into the applicability domain of the model, so a good definition of the applicability domain is essential, and the results are adequate for classification and labeling or for risk assessment. So the results are useful compared to what the specific scientific question is, as well as adequate documentation for the method is provided. So these are, let's say, the four keystone for using QSAR for regulatory purposes, even though, as I said, there can be different formulation of that. So again, the problem is about the adequacy of a prediction, and this comes from a valid scientific model, and of course, on the basis of the applicability domain, the model should be applicable to the query chemical, and these will identify a reliable result. But the model, it should be also relevant for the regulatory question or the regulatory purpose, because I can have a perfect model for an endpoint that has no clear meaning. I don't know if for a specific drug activity, I can have a perfect model for a specific drug activity, but this is not relevant for regulatory purposes, because that's not something interesting. And just when you have all these three pieces, you will have an adequate QSAR result for a specific chemical. So even though a model can be valid, it could be that it's not applicable to your chemical, or the model is not for a relevant endpoint. To define the validity of the model, there are the OECD principles for QSAR validation, which were an effort to improve transparency and acceptability of in silico methods. And they are quite general, but then there have been some documentation that is built on top of them. And so the principle states that you need a defined endpoint, an unambiguous algorithm, a defined domain of applicability, appropriate measure of fitting, robustness, and predictivity, and whenever possible, a mechanistic interpretation. So for the documentation, for the model itself, there's the QSAR model reporting format, which describes the, for the specific model, the 5 principles, how the 5 principles are declined in that specific models. And for the prediction reporting format is for the specific prediction, and nowadays, since last year, maybe 1 year and a half now, we have the QAF, QSAR assessment framework. This is more for regulators, but mainly you may see that from the QSAR model, you have a QSAR prediction and a conclusion on a property. For the reporting, for the model, we have the QMRF that usually is provided by the developer, and the QPRF, so the prediction that is usually derived by a QSAR user. And the assessor has some checklist for the model and the prediction to ensure the robustness of the conclusion. So this is the structure of the QMRF, which contains different specific information related to the 5 OECD principles. So some general information, and then some information about the endpoint modeled, the type of algorithm and the descriptors used for the models, how the applicability domain is defined, and then all the statistics related to the fitting and internal validation, the predictivity due to the external validation, and the reasoning about the mechanistic interpretation. And on this documentation, there are a number of assessment elements that are to be evaluated. I'm not going through the animation because then it's going to take too long, but for instance, transparency of the underlying experimental data, the quality of the underlying experimental data. So all these things are those that are important to define whether the prediction will be relevant or not. Okay, now I need to to move through all the animations. For the QPRF, you reason instead about the specific, okay, you have some information about the model and software, but it can be something that is taken directly from the QMRF, but you should reason instead about the substance. You are interested to predict which type of prediction is given back from the software. which input was used to obtain that prediction, the applicability domain and limitation of the model. And this point was recently added when the QAF was released, and is related to the reliability assessment. And then, of course, reasoning about the purpose of the use. So the point, as I said, is because for the applicability domain in the new QPRF, the applicability domain as defined by the model developers. So it can be that the model developers really didn't take a lot of care of defining a very precise applicability domain, so maybe just put some molecular weight range and that's all. And this part is compared according to that assessment, while the reliability assessment contains much more information related to the reproducibility of the output, whether the descriptor space or structural fragment space or the response space of the predicted compound is somehow overlapping with the training set data, and if there are information about mechanism or metabolism that may pose a relevant, that may have a relevant role in modifying the reliability of the prediction itself. Similarly, there is a checklist for the predictions, and again, it's very important to identify which is if the input is a representative of the substance under analysis, and if the input have reliable parameters, and so on. So again, I won't go through all these details because otherwise it will be too long and there will not be time for questions. So we don't have yet a clear idea, but I mean, there's also the QAF for multiple models, because usually it's better to use not just one model, but multiple models. And this implies that you need all the different QMRF, all the different QPRF, and then the QSAR results will be the combination of different predictions. We are still discussing just about integration of QSAR and not of QSAR prediction, and not, let's say, weight of evidence where maybe QSAR may be combined with read across or other information. And as take-home messages, I like to point out that all models are wrong, but some models are useful. This is an old quote by Box. And so the important thing is that maybe a QSAR model is not working 100% of time correctly, but there are ways to recognize when you can have a good prediction, a reliable prediction, and use them to avoid the experimental testing in some, for at least some of the instances you are interested to analyze. So there are several requirements that need to be satisfied to have a model prediction applicable and acceptable for regulatory purposes. And many of these issues should be targeted since the very beginning, already during model development and use, because later on it's not possible maybe to take care of that. And good documentation and good practices are essential to increase acceptability of the QSARs, even now it's gone over the PARC slide. And with this I conclude. Here are my contacts that are unreadable, but now I'll change the colors, and if you have any question, just let me know. And thank you for your attention.
Okay, thank you, Alessandra. I think that there have been some questions, and I replied with chapter 1.
Okay.
Is related to the availability of material, in particular books. So within Vega, we have developed the first ebook with, let's say, both the theory and then some exercise. And I put in the chat the link. And within PARC, we wrote a second ebook, which will be available in a few days. So the book is ready in practice. And so this again will, let's say, have one part with a new theoretical aspect, and particularly related to the new models and the examples which have been taken from PARC. And this session is recorded, and so it will be available, and the slides also will be made available. These are referred to another question, which was in the chat. I don't know if there are other
specific questions. I will correct some typo maybe before. Every time I go to the slide, I see them. So if there are... okay.
I have one question regarding regulatory purposes. We already have ECA guideline, OECD recommendation, and REACH mentions QSAR as acceptable under several conditions. Could you please indicate if you know any model that would better work for regulatory purposes?
It's not a matter of the model itself, but it's a combination of the model and the substance under investigation. So as I try to show you through the QMRF and the QAF, you have some rules that you need to satisfy for the model itself, but that will not be sufficient because the chemical and the prediction should also be, the model should also be applicable to the specific chemicals, so that also the checklist and the important things related to the prediction are taken into account. That's the common question. Can I have the one that it's working and use just that? Unfortunately, not. Because, I would also say, just my last bite, that if something is really working 100% of time, at that point, no more experimental tests would be needed. But I think we are quite far away from that.
Okay, so maybe we can have a coffee break until 11:15. We come back in 15 minutes. Hello. Welcome back. I think we can start. And now we are going to speak about entering into the details, and more in particular, now we cope the methodology, in particular regarding read-across. Read-across is widely used also for regulatory purposes, used since many years by industry assessors. And it means that we imagine that we do not have the toxicity value, I don't know, of ethanol, and we use the toxicity of methanol. So we look for similar chemicals, and we assume that the effect is somehow related. the one-to-one case is one possibility. It's better to have this kind of situation where we have more than one substance, in particular if they belong to the same family, for instance, if they are congeners. In this case, we are interpolating the value. In this case, we are somehow maybe extrapolating the value. Alessandro already mentioned the fact that we may have data of noisy data, we may have errors. If we refer if we to only to one substance, this is quite risky. It's surely much better to have more than one similar substance, if it is possible, to support our evidence. Read-across, as I said, has been used since decades by industry, by toxicology, by experts, and even for reach, most of the non-testing methods are using read-across. Only the minority of the non-tested methods is read-across. When I say non-testing methods, this, an official point of view, regards both the QCR part and the read-across, because we do not make experiments. It's a non-testing methods. But there are critical points related to read-across. So the reason is maybe rare. If you ask toxicology, this may be also expensive. This is surely subjective. It depends on the expert. Because each may have a different appreciation of the different studies that they read, and so they may provide assign different weights to the same feature. And they also have a different experience, so may be aware of something, not of everything. They rely on their experience, maybe they miss something. And there have been some papers documenting that this kind of approach is not reproducible, even in the case of experts starting from the same collection of paper to make the assessment. So the way that they read, they understand, they elaborate the result may be different. Let's think about the issue of glyphosate, which is assessed in different way in the States and in Europe. Similarity, you cannot define similarity based on one single item chemical. This is not a property that you can measure. You can measure many things, the weight, the time, whatever, not the similarity. You cannot physically measure similarity. Similarity is always a relationship between two things, not one, two or more. And similarity is related to the purpose. And so in particular, similarity for mutagenicity may be different for similarity for fish toxicity, for instance, because the endpoint can make the difference. So this is something quite important. And so it is not, there's no unique way to measure similarity. And on a mathematical point of view, similarity is a reflex. What is important that it is not transitive. So if chemical A is similar to chemical B, and if chemical B is similar to chemical C, you cannot conclude that chemical A is similar to chemical C. So you will see when you make a read-across, you will see that the relevance of similarity drops quite suddenly. So it may be, let's say, not a good idea to go too much beyond the really similar chemical, because indeed, on a mathematical point of view, this is the reason for the fact that the property is not transitive. It is quite useful to refer to this guidance done by EFS. We wrote a few years ago, but it's still quite valid and useful, related to read-across, related to in silico models, and also for other purposes. Generally, these are the criteria that apply to not only to read across in silico model, but at least it's quite a general guidance. So this is the process. At the beginning, gather all information, all the data, then evaluate individual line of evidence, and then integrate the result. That this is something quite clear, obvious, understandable. And how to integrate? There are three steps and three criteria: the relevance, the reliability, and the level of agreement. So if something really is relevant, is important for what we're speaking about, so again, it depends on the problem formulation, depends on the purpose. The reliability, if the result of in silico model, if the similarity is really similar or not. So this refers to the reliability. And then the level of agreement between the different lines of evidence. Level of agreement. Think about what we said in the introduction. Think about Galileo, the agreement between the theory and the experience. So starting from that guidance, we published this paper with people from EFSA, but also from SCCS, also under regulation. Kazim is the chair of SCCS, is the Committee for Cosmetics. This is freely available. And basically, it applies to what we said. So you may have multiple in silico model. This is good. You may have multiple similar compounds, and you should evaluate individually the results of individual model 1 to 3, checking if it is relevant, if it is reliable, and so on. So this is basically the process. Unfortunately, this process has to be done so far manually. We are working to implement this into a software in a certain level within one software, Swan. This has been done in a preliminary stage, but this has to be done manually. Tomorrow, we will see the exercise on how to do this in practice. But what should you look at? When you will use the Vega model provides 3 lines of evidence. One is the prediction, toxic, not toxic, toxicity is 3.4, whatever. Another one is the read-across. So Vega will show the 6 most similar chemicals. You have to look at these 6 most similar chemicals. You have to evaluate. This is a separate line of evidence. And then depends on the model. If some model have a mechanistic explanation, this is also provided. So you have 3 separate lines of evidence when you run each individual in silico model. So this is, as we said in the introduction, the virtual step. This is the experience, as I said, let's say the Aristotle. This is the Plato, so the theory. And ideally, all the 3 lines of evidence should be in agreement. This is the best way. This is the Vega website. We suggest you to go here and download the individual models and the QMRF. For instance, Standard mentioned the QMRF. There will be here in this session download also the ebook from with the exercise related to the PARC exercise. From here, from the community, if you go, for instance, there are different projects and partners, but if you go in the concert reach, you can download the ebook, but also other training material, videos, and tutorials regarding this. Let's have a closer look at the read across. We have three different, let's say, tools for read across. Actually, we have more than three, but we will see in this course three. One is ToxReader. You already mentioned it, Vega. Later on, Erika will present you Vera. ToxReader, I think, is quite simple. And how to use it? Well, you have to download the current data session, you need the Java installed, which is freely available from your computer. And then you simply need the smiles. So the structure has to be, let's say, written in the smiles form. If you don't know the smiles, use PubChem, search for the chemical of interest, and PubChem will give you the smiles. And then you have to select how many chemicals, how many similar chemicals, 1, 2, 3, 20. Okay, I suggest to use, I don't know, something between 6 and 12, 15. And then you select the endpoint. So it's quite easy. And the result is something like that. So you have this is quite interactive in HTML. You have the structure of the target chemical, which is here. And then circles represent chemicals. At the center, there is the target compound. And here you will see 4 circles close related to this one, 4, because in this case I've selected 4. If you select 10, you will see 10 on this circle. And then it's quite intuitive. These are toxic, and this is non-toxic. So this is something that you can easily understand. And if you click on the circle, you will see, okay, this circle is this chemical similarities provided, it is mutagenic and so on. The size of the circle is related to the similarity. So if a circle, I don't know, maybe here, this is smaller because similarity is lower. And if a chemical is present in more than one cluster, this is a represented dust. And then you also have this triangle. In this case, this is the situation of mutagenicity. It depends on the endpoint. And these are structural alerts. And so in this case, for instance, if you click at the triangle, you will have information regarding the structural alert. And so, for instance, this structural alert, if you click, is this one, and this is explained, you can read, and it says, okay, this is a structural alert associated to this more, but you can enlarge, okay, acylates. And so this is structural alert associated to toxicity. This is represented in this way. And also you have the prevalence of toxic or non-toxic compound. In this case, 83% of the chemical are mutagenic in this case. And also Fisher test. While here, this one, for instance, the prevalence is only 70%. So this is red, this is, let's say, pink. Also the color is associated to the prevalence of mutagenic or not mutagenic. And of course, the shape of the triangle and the color is related to the fact that we're speaking about adverse effect or not, and also the size. Maybe in this case you do not appreciate it, but it depends on how many chemicals with this structure are present. And if you click here, you can read all the 100 chemical containing this structure. So in this case, we have this fragment. So the phenols, most of the cases, in 70% of the cases, are not mutagenic. And here you can see 4, because I've selected 4 in this case, similar compounds, similar to the target, but they, all the 4 contain the phenol group. 3 of them are non-mutagenic, 1 is mutagenic. Well, in this case, we have 4 similar chemicals, similar to the target, but they do contain this moiety, this functional group in this case also. And all of them are mutagenic. So you can start make some reasoning regarding the role, the function of this components. This is a tool which is quite simple. And what we wanted to provide in this case is something that put on the table all the different elements, so all the similar compounds, all the reason for adverse effect, toxicity, so to go towards a more systematic and not non-subjective evaluation. I don't know if there are questions related to this introductory part. Okay, so maybe we can proceed with following presentation, which will be given by Erika. So I mentioned already 2 ways to make read across. We will see, in particular, in the following presentation, Vega and the similar compounds. Something more elaborated is ToxRead, and the last software that we have introduced is Vera, and which solves some of the issues present in ToxRead. Please, Erika, make your talk.
Hello, everyone. Can you see my screen? Yes?
Yes, yes.
Okay, perfect. So I'm Erika. I'm a PhD student at Mario Negri Institute. I'm going to show you one of the software we developed to perform the read across called Vera. As mentioned by Emilio, the read across applies the principle of similarity to assess target molecules in a data pool situation. However, there are several metrics of similarity and several approaches, several characteristics that can be considered during the process of selection of similar compounds. So in this presentation, I'm going to show you how Vera selects the similar compounds and make the final assessment. The classical read-across approach have some limitation. There is no single strategy to make the assessment, making it difficult to be reproduced. The results obtained by read-across depends on the subjectivity of the expert that make the decision. And in case of conflicting data of the similar substances, it's difficult to reach a conclusion. And during the process, it's possible to lose some important substances relevant for our case, leading to an incorrect results. And there is no clear way how to define the reliability of the assessment. So with Vera, we try to address this issue. First, Vera is an automatic workflow, so the results are always reproducible. And Vera considers several metrics of similarity and several aspects to make the assessment. And in case of conflicting data, Vera performed a grouping analysis in which considered the co-presence of several characteristics found in the molecules to understand which one is more relevant for the target compound. During the process, the loss of substances is limited, and there is a mathematical definition of the reliability of the assessment. So I'm going to show you the basic concept under Vera, and Vera considers both chemical and toxicological point of view to make the assessment. One of the characteristics of Vera are the entities that are the properties investigated individually to search for similar substances. These properties are, from chemical point of view, contain also information about physicochemical properties and so on, and are part of the unsupervised part of Vera. So the part of Vera with the aim to select similar compounds independently from the endpoint of interest. Another chemistry part implemented in Vera are the molecular groups. We implemented more than 100 molecular groups to be searched in target molecules and in similar substances. And this information is useful to select the similar compounds, as I said, according to the pure chemistry of compounds. But also we implemented some structural alert lists specific for the endpoint of interest. The structural alerts are part of organic molecules believed that are responsible to the adverse effect of the compounds. These rules are expert-based. So in that case, we implemented also the literature knowledge of the endpoint of the toxicity of the endpoint. So as I mentioned, Vera is divided into two parts: the unsupervised part with the aim to select similar compounds independently from the endpoint of interest, and the supervised part with the aim to provide the assessment. In this unsupervised part, we consider the entity, so several properties that can belong to the chemical world, such as the flexibility of a molecule, the steric hindrance, the reactivity, but also we consider some physicochemical properties and the biotic and biotic characteristics, such as the metabolic pathway that can occur in the target in similar substances, but also some degradability pathway. For each entities, we can define a specific chemical space specific for the entities in evaluation that we call the subspace. But to investigate the chemical space of each entities, we need a huge amount of data. For this reason, we collected more than 10,000 structures from different databases to cover all possible aspects of each properties we are evaluating to search for similar substances. So to do that, we built a matrix with more than 10,000 rows with the chemical structure. And each column is referred to a specific endpoint. So for each chemicals, we can have the one or more experimental value from different endpoints. Then, to analyze better the subspace created in this way, we perform a specific cluster analysis for each subspace to group the chemicals into two or more clusters. And the idea is that molecules, for the cluster analysis, molecules belong to the same clusters, share similar behavior for the property we are evaluating. So we then projected the target into each subspace, and we use the information retrieved that we can retrieve from subspace to select similar substances and perform the assessment. In particular, in the supervised part, we provide two different types of assessment, so two prediction. The first one we call Vera entities, in which we considered of course, the entities and the subspace, And selecting the endpoint of interest, we perform a logistic regression on each subspace to understand which one is more relevant for the endpoint of interest. Then we search for similar substances in each subspace, and the final assessment for each subspace, we perform a preliminary results in which we weight the experimental values of similar found in this way according to their similarity matrix that is specific for each entities. And then each preliminary results for the 12 entities are weighted according to the coefficient found by logistic regression. And in this case, we obtain the Vera entity assessment. We perform also another prediction, another assessment that we call Vera alerts. In that case, we consider a target, we call a target fingerprint. It means that we can collect in a binary fingerprint, so in a binary string, the information about the membership of the target for each cluster in each subspace. And then we select all molecules, all similar, that have the same target, the same fingerprint of the target. In this way, we have the compounds that at the same time are in the same clusters for each subspace of the target. Then we search for possible structural alerts, and we searching for molecular groups in target and in similar substances, calculating a grouping similarity, and also perform a reasoning part in which we consider the co-presence of the structural alert and one molecular group at time. And in this way, we can perform the Vera alert assessment. So after the unsupervised part and the supervised part with the two prediction, Vera provide a consensus of the two assessment with the reliability of that assessment. Vera is freely available. If you want to try it, you can download in our GitHub page. Please send us an email so we can provide you the password to download the folder. We also develop a graphical user interface so it's easy to the user to use and apply the Vera read across. You can perform, you can assess more than one molecule at a time in a batch mode. We implemented several endpoints, both for human and ecotoxicological point of view. And also we provide an Excel file for, as output with all the prediction summarized, but also a PDF output, specific one for each molecules assessed, with detailed information of how Vera performed the assessment. Now I'm going to show you some example of the PDF output. The first example I want to show you is regarding the bisphenol A. It is a molecule very interesting from several work packages in PARC. In that case, I assess the carcinogenicity of the BPA. At first, we have the summary of prediction of the Vera alert assessment, Vera entity assessment that are both concordant in defining the molecule as non-carcinogenic, with information about the reliability. In case there are some structural alerts, they are highlighted in the structure of the target compound. In this case, we didn't find any structural alerts. For the carcinogenicity, for example, we implemented the Benini-Bossa rule set. So some mechanistic rules that bring to the toxic effect. In that case, the BPA contains no structural alerts. Then we have the information about the molecular groups found in the target compound. They are highlighted in the target structure and are sorted according to the toxic prevalence of the group in our database. In this case, it means that the 50% of molecules that contain the quaternary carbon are toxic, are carcinogenic. So also looking at this point, we can see that the majority of the groups are related to a lower possible toxic effect of our target compounds. Then we have an overview of the subspace, the target projected in each subspace in each cluster, and information about the importance of each subspace related to the endpoint and the consideration, so the carcinogenic effect. And then for the entities part, we provide also the 4 most similar substances of the target independently from the endpoint. And so we have the smiles of the similar compounds. In that case, we have also the identity. So we have the experimental values of the compounds that we have. We have the information about the carcinogenicity endpoint, but also one of the correlated endpoints that could be the mutagenicity. So at the end, the expert could use also the information about an endpoint correlated in this case, such as the mutagenicity, to reinforce the hypothesis of the assessment that the expert made. The same is for all the 12 subspace, but also for the metabolic and the degradability pathway. We also provide information about the reaction that can occur in the target, and we provide also the product of that reaction. We are working also on implementing the possibility to evaluate the product of this pathway, because we know that the possible toxic effect could be associated with the product and not only to the parental compounds. The same for the degradability space. We have the information about the degradability pathway that can occur in the target. Then we have the information about the most similar substances found by Vera entities and used to make the assessment. We have the information, of course, about the experimental values for the endpoint chosen, so the carcinogenicity in that case, and the information about in which subspace these molecules is found to be relevant for the assessment. Then we have the part of Vera alert assessment. And also in this case, we provide the 6 most similar substances. In that case, I show you only 4. We have the information about the experimental values, the Vega similarity, that is a structural similarity, but also another metrics of similarity that we call grouping similarity, that take into account the presence of the same molecular group, the presence of molecular group in common and not with the target to calculate these metrics. But also we have also the information about the molecular groups found in similar substances. In this case, Vera Alerts is able to perform the assessment only looking at the first 10 most similar substances. It means that the 90% of similar compounds are concordant in the experimental value. In this case, the 90% of molecules are non-active, so the assessment of Vera Alert will be non-active. I want to show you another example, only to present you another part of the output of Vera. In this case, we assess this target molecule for the mutagenicity. We predict the mutagenicity. In this case, Vera alert and Vera entity, as before, are concordant in defining molecule, not mutagenic, with low reliability. Also, in this case, we have the information about the molecular groups sorted according to the toxic prevalence of the target. And also in this case, we have no information about, there is no structural alerts in the target. So we know that the aryl methyl groups is associated with more toxic compounds. So more than 60% of compounds that contain these groups are toxic. So in case of absence of structural alert, Vera use these molecular groups as possible toxic reason, possible toxicity reason, and perform the reasoning analysis, in which we can evaluate the co-presence of the most plausible toxic effects associated with the aryl methyl in this case, and one of the molecular group and time. In that case, I'm going to show you one example of this grouping analysis, and we see that molecules that have the aryl methyl groups and the sulfonamide are all similar, have the experimental values of non-active. So Vera used this information of the reasoning part to provide the assessment. The last example I want to show you is an isosorbide. we describe in detail how to assess this survived, also using QSAR models and several read-across approaches in the book of PARC that will be soon available, as mentioned by Emilio. Differently from the other endpoint, the fish acute toxicity LC50 is a regression endpoint, so we provide the continuous values of the prediction, and the consensus is the mean of the two assessments, and also we have the information about the reliability. In that case, I'm going to show you how to use the read-across output, how to use the PDF output. Indeed, the user should not looking at also the prediction, but also should use the information available in the PDF output as an additional line of evidence, as said before by Emilio. So in this case, I present you the first similar substances found by Vera entities. And in the book, we describe in detail, but we also can use this information, so the structure of similar substances found in different subspace and so on, to try to reinforce the hypothesis, the prediction of Vera. So in that case, we can see that, for example, the target is bicycle. So we have no similar substances that are bicycle. The most similar substances have a larger number of hydroxyl groups, so it's more soluble, so possible could be less toxic than the target. The other similar contain less number of hydroxyl groups, so it could be more toxic than the target. So the output could be very useful to strengthen the hypothesis of toxicity or not of the target. So to conclude, the read-across is a useful approach in case of data gap situation, and most important is recognized by regulatory agency to perform the risk assessment. However, the classical read-across approach is a very complex approach, so Vera try to help the user to screening similar substances that are provided in the PDF output. Is a well-defined workflow, so the assessment is always reproducible, and the assessment takes into account several features such as the structural similarity, the structural alerts, the molecular groups, the entity. So we can say that the results could be the all possible reason of toxicity or not are investigated in that case. So thank you for your attention.
Do you have questions regarding this presentation in general, read across? Okay. So maybe we can. Oh, okay. I see a question. How much similarity is considered sufficient for read across? This is a very good question. I think that with the exercise that we will have tomorrow, we will see different possibilities. Let's say that this depends, as I said in my introductory presentation on read across, there's no unique way to measure similarity, but there are some mathematical tools. And so the value actually depends on the tool, on the algorithm, the equation that you are using, so it depends on the software. In many cases, the value of 0.8, for instance, is considered as something good, for instance, if you are using Tanimod or something like that. Using the Vega software, the similarity we have a semi-quantitative, actually we have a continuous value as we will see to measure similarity. And we evaluate a good similarity if the value is 0.9 or higher using the Vega matrix. If it is something between 0.75 and 0.9, it's moderate. So if you are lesser than 0.8, for example, there may be some part in the molecule which are surely different. If the similarity is below 0.7, surely the two are quite different. But this matrix actually depends on many factors, how large is the molecule, and for example, here you've seen that Vera also uses, also other tools, the structure alert. So let's imagine that in your chemical you have epoxide. At this point, you may have a very simple chemical with epoxide, but also a very large substance with epoxide, but both will be, let's say, relevant, interesting, if you are evaluating epoxide. But the similarity surely will be very different. And the large molecule, for instance, will have a similarity value very quite probably less than 0.7. This regards the structural similarity, but it may be also depending on the presence or not of moieties associated to the similarity, and so this may vary. Another perspective, if you are using as within Vera, also physical-chemical properties. So maybe two chemicals with a different, quite different, very different structure may have a similar lockpit. I'm going to say something more in regarding the other. So you can download all the tools from this tool, from this link. You can download Vera, Vega. Here, as I said, I suggest I recommend you to download also periodically, because we have new versions. And how to use Vega, this I think is also quite simple. You have to insert the smiles, click here, so you can download if it is one by one, or if you have 100, you can import the file. And then you can select, actually, no, now the last version has more than 100 models. And so you can select the properties for toxicity, ecotoxicity, and you can select one or more of them. The kinetic are available. And so you can choose the model or the multiple model for the same endpoint. It is possible that there are more than one model for the same endpoint. We do recommend to use all the model available and not the single model. So it's good to have, as I said, different lines of evidence, because they will provide different elements for reasoning. We see the results are that it is quite common that the results are diverse using the different models. So please, not only one model for selected endpoint. And So for instance, for mutagenicity, just to have an example, some models are related, based more strong as model related to the collection of alerts which are associated, derived by the human expert because they are known to be related to mutagenicity. Think about the epoxide, aromatic amines, so on. There's a collection of mechanisms, while other models are more statistical based. And so it's good to have both line of evidence. Remember Plato and Aristotle, but also authorities, they do recommend, in particular for mutagenicity, to use at least two model covering both, let's say, the expert-based model based on reasoning and mechanism and the statistical model. Why? Maybe because the list of structural alerts, for instance, is not complete and actually depends on the tools that we are using in ESS, or there are other tools. The collection of structural alerts will be different. It's different. And there may be some missing structural alerts. So it's good also to have a prediction based on a diverse and large and extended set of chemicals using statistical tools. So based on the theory or based on the evidence of the observation and the statistical tools. So for instance, the SARPI model extracts rules, but based on statistical tools, for instance. And then you have to say, okay, the results, which may be a PDF, or if you have 1,000 chemical, a file, please save the file, independent if you want multiple files, a single file, where to put in the test, and then simply make a prediction. Each model, each Vega model, actually is not the model per se. It contains, you don't see, but it contains a separate parallel model. So one model makes the prediction, and the parallel model evaluate the reliability of the prediction. So each time you run a Vega, you run, even if it is one single model, apparently there are two models. One makes the prediction, the second one, the parallel one, makes the reliability. And so how this is done, Alessandro already mentioned the point of the applicability domain. So in the case of Vega, we have this tool for the applicability domain we call applicability domain index, which is a value ranging from 1, which is okay, it's very good, or 0, of course. But let's say this value should be something, again, higher than 0. This is quite good. If it is lesser than 0.75, it's low reliability. But this is a quantitative value. So in other tools for the applicable domain is evaluated simply as in or out. So it's 0 or 100. It's a yes or not. I think it's preferable to provide a quantitative assessment in order to move toward the probability, towards the quantitative evaluation, and this can be good also. Because for risk assessment, we need a quantitative way to evaluate this, and also for the way to combine multiple results. I think that it's more convenient to have a weight, a quantitative weight. But at this value, how is it say calculated? It is calculated based, depending on the model. In this case, based on these 5 individual checks, evaluations. So the software looks, okay, do I have similar compounds in the training data set, yes or not? Similar compound to the target. What kind of a prediction is possible on the similar compounds? Of course, the target compound principle is unknown. And what about the concordance between the experimental value of a similar compound and the prediction? And then there are some other parts related to the range of the value of the descriptor, and if there are, for instance, some unusual, not common fragments in my molecule contains germanium. This is unknown. I don't know. And in addition, Vega provides the most similar compounds. So you have these parts, the different parts are the cover. You see here the level of reliability, which is quite good in this particular case, for instance. So it's a 3-star, 2-star is moderate, 1-star is low, so it's questionable. And you see the cover in the summary in the case of mutagenicity, for instance, the prediction, if there are structure, this is indicated, and the check if there's something strange, not correct in the smiles, the software automatically verify and corrects, but provides a remark. Whenever format of the smile you introduce Vega, double check and transform into a canonical smile in some format. And then you see the 6 most similar compounds, number 1, with I don't know if you can read it quite low, but anyhow, the similarity between the target and the source compound, similar number 1, 2, 3, 4 for each chemical, and then the experimental value of the similar compound and the predicted value of similar. And so this is how the software works, the parallel software. But this piece of information, the similar compounds, they should be used by you independently. You must have a look at this similar compound. So regarding the reliability, there are this depends on the software. The list of these checks may vary if it is categorical or if it is quantitative value and so on. And basically, if you remember what Alessandra said, at the basis of a QCR, we have these 3 components: the chemical structure, the toxicity, and the algorithm. This is the point. And so our tool within Vega copes with all the 3 parts. What about the similarity considering the chemical part? What about the similarity considering the algorithm? What about the similarity considering the toxicological part? Most of the other tools for applicability domain only cover the chemical similarity. I think it's preferable to use all the 3 levels of similarity and reliability, because let's imagine that you have 100 chemicals to build up a model for mutagenicity, and the same 100 chemical to make a model for fish toxicity, for bioconcentration. Do you think that there will be outliers? Surely there will be some strange value. Do you think that this outlier for mutagenicity will be the same of the outlier for fish toxicity? Well, probably not. But on a chemical point of view, the similarity will be the same. I'm using the same 100 chemical, but epoxide, for instance, we said, is mutagenic, but regarding fish toxicity or regarding bioconcentration, of course, this will be read more or less as an ether. So the relevance of that similar chemical for mutagenicity or fish toxicity is not codified uniquely by the chemical, but the chemical plus this toxicological meaning. That's why we developed a more sophisticated tool for applicability domain that also covers this. Let's have a look at this because sometimes it may be not clear the difference between accuracy and concordance. So as I said, Vega makes in parallel the prediction of a similar compound. So this is our target. And in this case, we are speaking about carcinogenicity, for example. And the model say, okay, it's not a tox, it's not a mutagenic. And this is based on a neural network, so it gives a probability 92% is non-toxic, and of course 80% is toxic. And I have two similar chemicals. This is my target, a similar number one, similar number two. This is toxic, but there's an error in the prediction for this similar compound, because this model say, oh, this is non-toxic. The other chemical, this is non-toxic. But here again, this model for carcinogenicity, this is the neural network model, makes an error, and it predicts a toxic. So you see, in both cases, the prediction goes in the opposite direction. And so in this case, when you use this model, the Nick model for carcinogenicity, the model immediately say, look, here I have a big issue because I see that for this chemical, my model, this specific model, that doesn't work. So the accuracy will be 0. And so immediately it means that you cannot use the prediction of this model to evaluate this chemical. So this means accuracy. But by the way, as I said, you should always look at the similar compounds. So we can make this kind of exercise, if you allow me a couple of minutes. So what would you say? This is the target compound. Is it toxic or not? I cannot use this prediction. I said, the model immediately say, don't use it. But I have two other lines of evidence. Remember, I said, each model provides different lines of evidence. You should use all the lines of evidence. Line of evidence number one, prediction. You cannot use. The model immediately says that don't do that. But what about the other one? So what would you say? Sorry, just some water. The chemical similarity is quite similar. What I see that we have this moiety, we are like moiety here. Here I have two metals which are missing here. Personally, I think that this makes a difference. Here I have a metal in para. Here I have a metal in para. Here in para I have a chlorine, while here it is in metal. What I would think is that because here I have this chemical with a chlorine in a different position, but this is toxic chemical number. Sorry. Get the pointer, but this chemical which is toxic, what is the difference between the two? The presence of chlorine. So maybe I can guess that chlorine, think to benzene ring, is associated to effect, because this is the only difference between these two chemicals. And indeed, I can copy and paste this structure, run the other models for carcinogenicity, I always said, please always use all the model, and immediately running the other model, the ESS model. The ESS model will immediately say, okay, look at this. I found the structure alert for this chemical, which is the chlorinated benzene, which is not present here. So immediately using the multiple model, using the multiple line of evidence, including the results of this, the better results apparently of this model, you can get the conclusion that this target compound is carcinogenic looking at the similar compound. But anyhow, the accuracy here is low. What about the concordance? The concordance, the meaning is this one. This is the target compound, and it is predicted for, in this case, it is possible non-mutagenic. So the model say it's not mutagenic, but look, I have an issue here. The model says immediately, the concordance is low. What does it mean? The prediction is non-toxic, but I have chemical similar number 1, similar number 2 also, and they are toxic, they are mutagenic. So there's no agreement between the prediction and the experimental value. Previously, we were discussing of the agreement, between the prediction and the experimental value of the target of a source compound, of similar compound. In this case, the prediction is correct, mutagenic, mutagenic. Here, correct, mutagenic, mutagenic. Here is correct, mutagenic, mutagenic. This is accuracy of the prediction of the chemical which are in the training set in the test. Here I'm speaking about not the agreement of a prediction, but of the similar compound, but agreement of the source compound, the experimental value, and the target compound. And so you can see here, I have a problem because I predict something, but let's say read across, we can read, thinking in this way, the prediction says something, but read across says something different. Again, you can also evaluate and discuss this. Vega provides a warning, so say reliability is not so good, but you can overcome this kind of warning. Why? Because again, Vega helps. Vega says that, look, this chemical has an alert, actually 2 alerts, which are not present in the target compound. The target compound has the 2-phenol and this double bond. Here I have the amino group, and also here the same. And so the system says, look at these 2 similar compounds, they are not relevant, if you remember what we said regarding relevance and reliability. So we should disregard chemical number 1, we should disregard chemical number 2, because yeah, they are aromatic amines, and aromatic amines are mutagenic. But this is not of interest. We're speaking about the phenols. So the concordance is not, we can overcome. We have to look, we have to evaluate. But we can, at this point, disregard, then maybe we can have a better look at the similar number 3, similar number 4. And this is non-mutagenic, and this is non-mutagenic. So there is agreement. Maybe it can further discuss this. Okay, this. Here I have ethyl and ethyl, which is not present here. So maybe I can think of that this chemical, I can imagine a nucleophilic attack to this double bond, because here I have the phenol, and so the electrons can be attracted here, and so this facilitates the nucleophilic attack here. But it cannot occur in this case, because quite probably it's more limited for steric consideration. And so maybe you can say maybe the reliability of this similar compound is not so high. Maybe yes, maybe not. Because you should look at chemical number 4. Chemical number 4 has the same double bond in ortho to the phenol. But this is not mutagenic. So I can disregard this level of, let's say, additional warning that may have, looking at all the similar compounds. So this is simply to say that you should very carefully evaluate all the lines of evidence, all the warning. You may disregard after, but provide an explanation why you may disregard this kind of concern. And at this point, you can get a conclusion and describe, but using the multiple, remember, always line of evidence. Okay, do you have questions? No, but in any case, tomorrow we will have many more examples, many more reasoning about the way to use the multiple lines of evidence. Okay. I thank you for participation to this meeting. Even if later on you have questions, please write. Always, anybody can write to Vega, asking questions regarding how to use, how to interpret Vega. And tomorrow we will continue with more examples and explanation and exercises. Thank you for your participation.
Thank you.
Thank you, I.